Data protection requirements change depending on whether information is moving between systems or sitting in storage, and confusing these contexts often leads to gaps in protection. Data faces different threats when it is transmitted across networks than when it resides on disks, backups, or endpoints. In transit, the primary concerns involve interception, manipulation, and impersonation. At rest, the concerns shift toward unauthorized access, loss of media, or improper reuse of storage. A mature security program treats these contexts separately while ensuring they work together as part of a single protection strategy. Understanding the distinction allows controls to be applied intentionally rather than generically. Before we continue, a quick note. This audio course is a companion to the CISSP books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Data at rest includes information stored in databases, file shares, backups, archives, virtual machine disks, and endpoint devices such as laptops and mobile phones. This data may sit unchanged for long periods, but that does not mean it is safe by default. Threats include stolen devices, compromised administrators, misconfigured storage services, and improper disposal of media. Copies of data at rest often proliferate through backups and replicas, expanding the exposure surface without obvious visibility. Protecting data at rest therefore requires thinking beyond primary systems to include secondary and tertiary storage locations. When at rest, protection is incomplete. Organizations often discover exposure only after loss or misuse has already occurred. Data in transit includes network flows between users, applications, services, and infrastructure components, whether inside a single environment or across external networks. This includes web traffic, application programming interface calls, file transfers, email, and system-to-system synchronization. Data in transit is vulnerable to eavesdropping, man-in-the-middle attacks, replay, and injection if not properly protected. Even internal networks cannot be assumed safe because lateral movement is a common attack technique. Treating internal traffic as inherently trusted is a frequent source of breach impact. Protecting data in transit is therefore essential even within controlled environments. Encryption at rest protects confidentiality when storage media is accessed improperly, such as through theft, loss, or unauthorized system access. By encrypting stored data, organizations ensure that possession of the media alone is not sufficient to read its contents. This protection applies to databases, file systems, backups, and portable devices alike. Encryption at rest is especially important for mobile endpoints and removable media, which are more likely to be lost or stolen. It also provides a safeguard against misconfiguration that exposes storage unintentionally. Encryption does not replace access control, but it provides a strong second layer when other defenses fail. Encryption in transit protects data against interception and manipulation while it moves between endpoints. Without encryption, network traffic can be observed or altered by attackers positioned anywhere along the path. Encrypted channels ensure confidentiality by making captured traffic unreadable and integrity by detecting tampering. Encryption in transit also supports authentication, helping systems confirm they are communicating with the intended party. This protection is critical on public networks, but it is equally important within private networks where attackers may already have a foothold. Consistent use of encryption in transit reduces reliance on network trust assumptions. Integrity mechanisms complement encryption by detecting unauthorized alteration of data, ensuring that what is received is exactly what was sent. Hashes provide a compact representation of data that changes predictably if content is modified. Digital signatures combine hashing with cryptographic keys to provide both integrity and source verification. Authenticated protocols ensure that messages cannot be altered or injected without detection. Integrity protection is essential because encrypted data that is modified undetected can still cause harm. Together, encryption and integrity mechanisms protect both confidentiality and correctness. Key management is the foundation that makes encryption effective, governing how cryptographic keys are generated, stored, rotated, and accessed. Weak key management undermines strong algorithms because compromised keys render encryption meaningless. Keys must be protected from unauthorized access while remaining available to authorized systems and processes. Rotation policies reduce the impact of key compromise by limiting how long any single key is valid. Access controls around keys enforce separation of duties and prevent misuse. Effective key management transforms encryption from a checkbox into a reliable control. Access control limits who can read or modify stored content, ensuring that encryption is not the only barrier protecting data. Access policies define which identities are permitted to view, change, or delete information based on role and business need. These controls apply at multiple layers, including applications, operating systems, databases, and storage platforms. Strong access control reduces the likelihood that encryption must be relied upon as the sole defense. It also supports accountability by linking actions to identities. When access control is lax, encryption alone cannot prevent misuse by authorized but inappropriate actors. Secure protocols provide encrypted channels with authentication and negotiated algorithms, allowing systems to communicate safely without manual configuration for each connection. These protocols establish trust, agree on cryptographic parameters, and protect data automatically once sessions are established. Proper protocol selection and configuration matter because outdated or weak options can negate protection. Secure defaults reduce reliance on individual judgment and prevent accidental downgrade to insecure methods. Protocol enforcement ensures that sensitive data is never transmitted in clear text. When secure protocols are used consistently, protection becomes systematic rather than situational. Data handling policies define where sensitive data may be stored or transmitted, translating classification decisions into enforceable rules. Policies may restrict certain data types from being stored on endpoints, removable media, or unapproved cloud services. They may also prohibit transmission over specific channels, such as unencrypted email or consumer messaging platforms. These rules ensure that encryption and access controls are applied in appropriate environments rather than assumed everywhere. Policy-driven restrictions reduce accidental exposure caused by convenience or misunderstanding. Clear policies make it easier for users and systems to comply consistently. Segmentation reduces exposure by limiting the paths data can travel within networks and environments. By separating systems and networks based on function and sensitivity, organizations constrain how far data can move if a system is compromised. Segmentation also limits who can observe or intercept traffic, reducing opportunities for abuse. In storage contexts, segmentation restricts which systems can access sensitive repositories. This layered approach complements encryption by reducing reliance on a single control. Effective segmentation turns breaches into contained events rather than enterprise-wide failures. Logging supports accountability by recording access to stored data, transmission events, and enforcement of handling policies. Logs provide visibility into who accessed data, when it was transmitted, and whether controls were applied correctly. This visibility supports detection of misuse, investigation of incidents, and verification of compliance. Logging must be protected to preserve integrity and prevent tampering. Review processes are as important as collection because unexamined logs do not reduce risk. When logging is integrated with data protection controls, accountability becomes measurable. Backup encryption extends protection to copies and replicas that are often stored in different locations or managed by different systems. Backups frequently contain large volumes of sensitive data, making them attractive targets. Encrypting backups ensures that compromise of backup media does not expose content directly. This is especially important when backups are stored off-site or in cloud environments. Backup encryption must be coordinated with key management to ensure recoverability when needed. Protecting backups closes a common gap where primary systems are secured, but secondary copies are not. In conclusion, protecting data in transit and at rest requires combining encryption, access control, integrity mechanisms, and disciplined P governance. Each context presents different threats that must be addressed intentionally rather than generically. Encryption protects confidentiality. Integrity mechanisms ensure correctness, and access controls limit exposure. Secure protocols and segmentation reduce reliance on trust assumptions in networks. Policies and logging align technical controls with governance and accountability. When transit and rest protections work together, organizations preserve trust in their data wherever it moves or resides. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.